Hi, my name is Chris, and today we're talking about working with exponents so that you can be awesome at maths. In today's lesson, we're going to talk about generalizing the properties of exponents. And if you haven't already noticed, we're going to be including some letters into maths today. Today we're going to learn about one of the several laws of exponents, the product rule. Now, before we get to letters, we're going to start with numbers and work our way to those letters, all right? In maths, we call this generalizing. So let's look at the number 32, and we're going to summarize the last couple of lessons we've just done. And 32 can be broken down like this, and then we can write it as a product of its prime factors like this, and then we can simplify it to this. Whoa, now hold up just a moment. I want to dissect this answer just a bit further so I can show you a couple of neat things about exponents and what we can learn from this. It's pretty simple here to say that I have 5 2's in repeated multiplication, so I can simplify that to 2 to the power of 5. That's all good, but, we are curious people and we want to do hard crap like 5 to the power of 27 times 5 to the power of 11. And we would like to do that quickly without having to expand and count all the time. In mathematics, what we try to do is look for patterns, learn from them, and then come up with methods or rules to make harder problems easier. Generalizing. I could start with 2 2's times 3 2's. Or I can look at 1 2 times 4 2's. In fact, there are 4 ways I could arrange this set of 2's. Take notice of the exponents on the left side of the equal sign. Look at that compared to the exponent on the right side of the equal sign. Can you see a pattern? Pause to think of it yourself, and then press play when you're ready. Alright, let's see if you notice the pattern. Let's strip away everything from the problem except for the exponents, and then we'll look at the exponents on the left-hand side of the equal sign, and then the exponent on the right-hand side of the equal sign. If you thought that the exponent on the right was the addition of the 2 exponents on the left, then you're correct. If you got that right, slap that like button for this video. If not, slap that like button anyway, and subscribe to become awesome at maths. Alright, look, before we move on, I have to make something very clear, and this is where a lot of students go wrong. The rule that we just looked at only works when the numbers in the base are the same. Remember our last lesson? Here's the base. This is really important, because numbers with different bases cannot be combined in the same way that we just did with the 2's. Look, here are a few examples.
Don't even think about it. Illegal. Don't do this ever.
In this lesson, we are talking about the product rule. The word product in mathematics is used for the result of multiplying 2 or more numbers. So, for instance, 3 times 4 is equal to 12. We could also say that 12 is a product of 3 and 4. So, products are all about multiplication, and so the product rule is only about multiplication. So don't go using this for addition, subtraction, or division. When multiplying 2 numbers that have the same base, their exponents, whatever they are, can be added, resulting in a simpler form. Alright, look, we're going to do a harder example in just a few moments, but I want to show you something that's just a little mind-blowing. Yeah, so that example I gave you before with all of the 2's, I said there were like 4 ways of writing it. Well, that may not have been completely true. We can write it like this because 5 plus 0 is 5. 6 plus -1 is 5. -16 plus 21 is 5. And yes, going to some fractions, 6/4 plus 7/2 is 5 as well. In fact, there's an infinite amount of ways that we can make 2 to the power of 5. What can I say other than...
I like to have fun, 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 fun!
Well, with this new way of looking at exponents, we can actually write 2 to the power of 5 in many different ways. All right, let's do an example together. I think we're pretty well equipped at this point to smash out a problem like this. Let's work the first lesson question out. All right, I see we have some exponential terms and they're being multiplied. All right, so that's a good first step here. Next, check that the bases are the same. And it looks like, yep, they're both 16. All right, so now all we have to do is add the exponents. A simplified way of writing this is 16 to the power of 58. Wow, massive.
OMG.
I tried to put it in an online calculator and I think I broke the internet. Alright, well, I think maybe we need a brief intermission. I thought I'd start off this next section with a meme review. Got like a young SpongeBob? I like how he's like a rounded head kind of thing and big eyes and lashes.
Yeah, I'm just learning the alphabet kind of thing.
X and Y in genetics. I'm assuming this means chromosomes. I don't know why he looks all mad like that. Yep, pretty much X and Y in math, so now we're getting pretty,
Yeah, this is big brain time.
Finally. I don't know if you guys know this about me or not, but I'm kind of a big Minecraft buff. I love Minecraft, and it's funny, X and Y in Minecraft for the coordinates. There's also a Z coordinate to tell your up and down position, which is quite useful when you're mining.
Nerd alert!
Anyway, that's our meme review for right now. Let's get back into the lesson. Alright, look, I know we've been talking a lot about numbers, but now it's time to bring some letters into the mix. Now, Chris, why would we do that? I don't know, because I like to
Have fun.
Now, we do this thing in mathematics called generalizing. And I did it before, and you probably didn't even realize I did it. I couldn't possibly write down every single number and combination. In this, A could have been 5, or it could be 7, or it could be pi. The exponents could also have been anything as well. And in this case, this is why we use letters. Look, the point is, in mathematics, we don't always know what number is going to go into what place. All of this depends on the types of problems that we're solving. So instead of writing down all of the different possible numbers we could have, we just simply write down a letter. Okay, so in maths, we use letters to represent a number, or value, or quantity that we don't know. Sometimes we call this an unknown. Letters are also used when a number is dynamic, or changing, but that is a little more advanced for our needs right now. The main point here is that letters represent numbers, and they behave and follow the same rules that numbers do. So when you learn a rule for numbers, that will generally translate over to letters as well. We're now going to touch on some algebra a bit. In algebra, we have this phrase, like terms. Like terms are letters or numbers that are the same. In algebra, we can only add like terms. So for instance, if I have a plus a, I can simplify this to be 2a. If I have a plus b, well, there's nothing more I can do here because a and b are not like terms, therefore I cannot add them together. So I just leave it as a plus b. Alright, that was a fairly simple example, but what happens when we get to more difficult things like, say, b to the power of 23 times b to the power of 45? So let's go back to our two examples and modify. So we have a times itself 5 times. Now with the 2's, it didn't look so bad. But now that we are using letters, the multiplication signs look really confusing, which is why we don't use multiplication signs in algebra. It is beneficial to us, and to others, to simplify this mess into something that is more readable. We will use our rule for simplifying repeated multiplications. I have a times itself 5 times, so that becomes a to the power of 5. Let's look at the rule to see if it works. As it turns out, our rule still applies the same way, even if we are using letters. So, let's apply this to our ridiculous example. I'll just pull that up. And this is our answer. Alright, to solidify our understanding, let's just do a couple of examples with numbers and letters. I'm going to show you the problem, and then after 2 seconds for each of these problems, the answer will come up. I'm really encouraging you to pause the video, try and get an answer for yourself, and then check it when the answer comes up. Five to the power of 7 times 5 to the power of 8. That's 5 to the power of 15. 12 to the power of 7 times 12 to the power of 3. So altogether we have 10 12s that are multiplying each other. So I'll write that out as 12 to the power of 10. Here I have 10 to the power of 7 times 11 to the power of 12. This cannot be simplified because the bases are not the same. This is much more tricky. We have 3 to the power of 7 times 4 to the power of 2 times 3 to the power of 3 times 4 to the power of 5. The trick here is to group the bases that are the same together. So for instance, I have 3 to the power of 7 times 3 to the power of 3. That becomes 3 to the power of 10. Now looking at the 4s, we have 4 to the power of 2 times 4 to the power of 5, and so that becomes 4 to the power of 7. Alright, looking at some letters now, we have f to the power of 17 times f to the power of 33. Big numbers, but no challenge for us at this point. We just take 17 plus 33, that's 50, so we'll end up with f to the power of 50. Alright, this last one looks pretty tough. We have a to the power of 17, b to the power of 12, times a to the power of 50, times b to the power of 15.
Maximum effort.
Alright, we group the a's together, so I see I have a to the power of 17, a to the power of 50, so 50 plus 17 will be 67. And for the b's, we have b to the power of 12 and b to the power of 15, so 15 and 12 is 27. So what I'll get in the end is a to the power of 67 times b to the power of 27. Did you get them right? Well, if you did, slap that like button right now. If not, slap that like button anyway and subscribe to become awesome at maths. Let's just recap. What did we learn today? In this lesson, I demonstrated one of the several laws we have for working with exponents, the product rule. We found out that when we multiply like terms together, we leave the base alone and we add the exponents. Also, this only works for multiplication and not for any other operation. Well, I leave you with the lesson questions that we started off with in the beginning. As always, thanks for watching and I hope it helped.